This is Machine Learning Foundations for Product Managers, final project, looking at modeling approach, model building, model evaluation, model interpretation. This modeling task is a supervised regression problem. We have continuous numeric data. The data is labeled values listed for the target variable. We looked at three algorithms, multiple linear regression to create that baseline, see how the features interact, ridge regression, um, an evolution of linear regression that uses a penalty to keep coefficients small, prevents the model from being too sensitive to noise. And then we looked at random forest regression, which is an ensemble method that uses a forest of decision trees. In this case, we used 200 decision trees. It captures nonlinear relationships that a straight line just can't see. Uh, we imported our data, did a data sanity check. We counted total rows. We looked at some of the key statistics, and then also determined that minimum values for features like ambient pressure and temperature are within the expected physical range, meaning they're not zero, suggesting that there's no sensor dropouts. In this case, we're going to build our three models. This first model is the linear regression model. And then when we evaluate those models, we're going to do that by looking at the residual plot, the R-squared error, and the root mean squared error. So in this case, we used 5 folds for our linear regression. We ran that, and let's take a look at the results. And there'll be similar uh, analysis as we move through all of them. The R-squared 0.9287. Our baseline model explains approximately 93% of the variance in net electrical power output. The root mean squared error, 4.56 megawatts. So on average, the baseline model's predictions deviate from the actual output by about 4.6 megawatts. We do see on this residual plot at the low end of the power scale, power output scale, and the high end of the power output scale, it becomes inconsistent, and certainly appears that we have a linear limitation. As our simplest model, the straight line estimator shows a clear inability to bend the physical efficiency curves of the plant. We applied ridge regression, and we looked at regularization strengths of 0.01, 0.1, 1, 10, and 100, and ran our same analysis. And we see a very similar result. R-squared 0.93, root mean squared error 4.5. So we're about 93% of the variance explained. And on average, the model's predictions deviate from the actual output by about 4.5 megawatts. We still see at the low end of the predicted power output and the high end of the predicted power output inconsistent reliability. We then went to random forest. Again, we had 200 trees in our forest, and we used bootstrap sampling using a random subset of features of data for each split. And let's take a look at those results. All right, here we see R-squared 0.9640, root mean squared error 3.23 megawatts. So this improvements in both areas, the variance and the error, both improved. But when we look at that residual plot analysis, we see the elimination of that U-curve, a straight error trend, and accuracy at the extremes. So our final model interpretation and conclusion, our table above, it shows the final test performance of all three models using consistent evaluation framework. The random forest model achieved the best overall performance with the lowest root mean squared error and the highest R-square on the held out test set. This indicates it explains a larger proportion of the variance in net electrical power output while making significantly more accurate predictions. The linear and ridge models exhibited that distinct U-shaped curve in the residuals, just visual proof of model misspecification, where the model fails to capture the nonlinear physics of the power plant. We did see that temperature was the largest indicator, and this aligns perfectly with thermodynamic principles as temperature directly impacts density and combustion efficiency. So this model's logic matches physical intuition and increases our confidence in its validity. Looking ahead, we could look at things to improve our simpler model, like implementing polynomial features by transforming inputs into higher order terms like temperature squared. Then we can then bend that linear model to fit observed curves without the overhead of a forest model.